Good morning or afternoon, whenever you're watching this video. Um, I'm sorry that I'm not here today. It wasn't planned. My son is still sick. Couldn't get him into the doctor yesterday, so the first appointment we can make is today. So I apologize. I didn't want to be out because obviously we're coming down to the wire. For you guys who are planning on coming and doing corrections today, we'll just have to delay that one day, and you can come in on Wednesday because I will definitely be back. What we're doing today is graphing. I don't think you're going to struggle with it, but like I said yesterday, if you do, we will just back up our test. Instead of Thursday, we'll take that test on Friday. So what I want to do is I want to work through all the ones that are on the back of this worksheet because I thought they were a little bit more challenging. So real quickly, let me just kind of flash these up so you can quickly check to see that you did all the ones on the front side right. They were a little bit easier, so hopefully you guys did okay. Here's number 2. You can tell I subtracted 15. Then I got rid of that square root by squaring both sides. Then I just solved the problem, as you can see, and got the value 45. I plugged 45 back in, and remember, this is just straight calculator. Just go type in the square root of 4 times 45 minus 11, and then scroll outside just to the right and put plus 15, and it gives me 28. That is not equal to 2. Therefore, the answer cannot be 45. It's extraneous. Let's move on to number 4. Again, just went through the process of solving. Remember this right here. This was my rational exponent that's treated kind of like a radical. That's what I've got to isolate. So I added that 11, got 6. Then I got rid of that. Remember, it's all about the root when it's a rational exponent. The root is the denominator of that fraction. So we square both sides, and then you solve by subtracting 7. I went and plugged 29 up here, as you can see, and sure enough, that gave me negative 5. So they were equal. This is the solution. Here is number 6. 6 might have been a little bit harder. It wasn't too bad, but you had to subtract 17. That gave me negative 16. Then I divided by negative 2. That will cancel that negative out and become a positive 8. Then again, we raise it to the power of the root. That's squared. So that gives me 64. Subtract 10, divide by 3, x equals 18. I went straight to my calculator. Look, I just typed this into my calculator. I replaced x with 18. So 17 minus 2 times square root of 3 times 18 plus 10, pushed equals, and sure enough, 1 equals 1. And then the last one on this side, again, was kind of like the top one on the other, except they were both fractional exponents, which works the exact same way, like we said, as radicals. Remember, it's all about the denominator of that fraction. That is your root. So to get rid of it, we raise both sides to the power of that root. Okay, so I solved it there. I added x, that gave me 4x. Then I added this 21, that gave me 40. Divided by 4, x equals 10. Plugged it into both sides, it gave me about 2.08. Those are both equal, so obviously it is a solution. All right, like I said, I want to spend just a little bit more time on these problems on the back because they were a little bit more challenging. Number 10 was kind of borderline. So there's really 2 lines of thinking here. You could have gone ahead, since there's really nothing I can do with these. You could have gone ahead right now and gotten rid of that radical. But I don't really love working with fractions, like I know you don't either. And remember, how do I get rid of dividing by 2? So that's what I did. I multiplied by 2 to go ahead and move this on over. And that left me with the 4th root of 7w minus 5 equals 2 times the 4th root of w minus 2. Didn't make a huge impact in the problem itself, but it did leave it in a way that we're a little more familiar with. Now, of course, we can go ahead and get rid of that root by raising both sides to the power of that root, and that's 4. Now, on the left side, there's nothing else except that 4th root of 7w minus 5. So they cancel, and 7w minus 5 comes on down. On the right side, though, remember, 2 is not under the root. So it's not just going to come down like the rest of them do when the roots and the exponents cancel each other, you actually have to raise 2 to that fourth power. And that's 2 times 2 times 2 times 2. That's 16. But then that w minus 2 just kind of falls out. So what we really have here is we have 16 times w minus 2. Well, again, if I distributed that, 16 times w is 16w. 16 times negative 2 is negative 32. So now we've got this thing kind of in a position where we can solve it. I'm going to subtract 7w. So negative 5 will equal 9w minus 32. And then you're just solving a problem. You're adding 32, that gives me 27, equals 9w. I divide by 9, that's giving me a w value of 3. So that's the process of solving. Now let's check it real quick. Again, remember, checking is just straight calculator. So you're going to go to your calculator, you're going to go alpha y equals number 1, get your fraction bar. Then you're going to do 4 math 5 to do that fourth root. But you're going to type in 7 times 3 minus 5 up top. And then in the denominator, you're just going to put that 2. Now push equals. What did you get? You got 1. Okay, go to the other side. You're going to do 4 math 5 to do the fourth root of, and then you're going to do 3 minus 2, which y'all know that's 1. So fourth root of 1 is also 1. So sure enough, it works. So that is my solution. It is not extraneous. So hopefully that makes sense, and maybe you got that right, and if you did, awesome. Okay, this one. We have one kind of like this, but I believe in the examples it actually had a radical. This one's written as a rational exponent, but you notice how there's nothing else on the side of that rational exponent besides what's inside those parentheses. That means this thing's ready to go. So we're going to raise this thing to the power of the root. Now don't forget, the root, when it's a rational exponent, is the denominator. So we're going to raise both sides to the power of 2. So we're left with n squared equals, remember these cancel, and that leaves me with 12 minus n. Now we had one that was almost identical to this yesterday. Remember, because we have this n squared and we have this n, we actually have to solve this by getting everything on one side and then solve by factoring. So the n squared, since that's my biggest exponent, I'm leaving it b. I'm going to move this minus n by adding it. And I'm going to move this positive 12 by subtracting it. So sure enough, we're left with n squared plus n minus 12. That's a trinomial, and we're going to factor it by, or into 2 binomials. Remember the rule? We're going to take and find what multiplies to get n squared. That's n times n. What multiplies to get a negative? That's a positive and a negative. So they're working against each other. So we're looking for the two numbers that multiply to get 12. And those same two numbers combine to get that 1 right there, because that's a 1n. What two numbers multiply to get 12 have a difference of 1? Well, that's 4 and 3. It's got to be 4 and 3. And more specifically, to give me a positive n in the middle, it had to be positive with my bigger factor, 4, and the 3 with the smaller one, or the minus. So then if I take these two and set them equal to 0 and solve, this one I'm going to subtract 4, and this one I'm going to add 3. So my two solutions that I need to check are negative 4 and positive 3. Now, I'm going to go back up. I'm going to erase all this stuff that I had done up here because I need to type these in. Well, on the left side, of course, it's just n. So when I try that first value, that's just negative 4. But on the right side, type in open parenthesis 12 minus negative 4 raised to the 1/2. So if you go type that into your calculator, of course, the left side's negative 4, but that right side, that's going to be 16 to the 1/2. That's going to be square root of 16, which is positive 4. Do those two match? Well, of course not. So this answer is extraneous. Much like the one that we did yesterday in class. Okay, the next one. Again, remember, n is 3. So the left side, we plug the 3 in. Then on the right side, we do 12 minus 3 raised to the 1/2. So if you go type that in your calculator, if you do it in your head, 12 minus 3 is 9. 9 to the 1/2, or the square root of 9 is, sure enough, 3. That one's right. So my solution here is n equals 3. Okay, that's number 12. We're going to move along so we can get on to our notes pretty quickly to number 14. Now, some classes we did not get a chance to do the example that was like this on the review. So I need to, or on the note sheet, sorry. So I'm going to go ahead and try to work this through so you guys understand it. It's pretty easy because, look, this square root here, it's already by itself, okay? That's c plus 4 over there. I can't do anything with that. So I've got to go ahead and square both sides to get rid of that radical. There's a bunch of bad words that I could not get through there. Get rid of that radical. So that allows that radical to just cancel out, and 6c plus 15 drops down. Now here's the deal with the c plus 4 squared. Remember, that's a binomial. A binomial squared means we have to take it and multiply it by itself. So remember, leave the 6c plus 15 alone. Remember, we've got to use distributive property. So I've got to do c times c, c squared, c times 4, that's 4c. Then this 4 times c, that's another 4c. And then 4 times 4 is a positive 16. Now don't forget, and I'm going to go ahead and erase this. Hopefully you're following along. This 4c plus 4c, those are like terms. I'm going to make that 8c. Now, everything's looking pretty good. It's a little chaotic, but remember, because we have the c squared and we've got some c's here, we're going to just, instead of trying to solve for c by just getting it alone, we're going to get it all together. So I'm going to do that by subtracting this 6c, and obviously I'm going to subtract it from the 8c. They're like terms. And I'm going to subtract this 15 from the 16. This will allow all this to cancel, move to one side, and here's what we're left with. C squared. 8c minus 6c is plus 2c, and then 16 minus 15 is plus 1. So very much like the last problem at this point, we're going to factor. To multiply to get c squared, what do we got? C times c. To multiply to get a positive, remember they're either both positive or they're both negative. I look right here, they're both positive. So we're looking for the two numbers that multiply to get 1, but they combine to get 2. Well, that's definitely 1 times 1. 1 times 1 is 1. 1 and 1 combine to get 2. So look, we've got the same factor. So really, there's only need to take one of them and set it equal to 0 and solve. So we're checking negative 1. Okay? So again, go back up to your original, and let's plug it in. We're going to take the square root of 6 times negative 1 plus 15. Push equals. When you do that, you should have gotten a positive 3. Now on the other side, you're going to do just c plus 4. So negative 1 plus 4, sure enough, also 3. This works, so this is my solution. Okay? There's number 14. Let's go on to the last one, and we did this problem in, I think we did this in every class. It may have been a little rushed in 4th period, but I'm pretty positive we did this. Again, you've got a square root on this side, and you've got a square root on this side. Now that plus 7, that's on the outside, moving that doesn't really help me at all. So therefore, we've got to move to step 2, where we're going to get rid of the square roots. And we get rid of the square roots by raising them to the power of the root. Now, on the left side, no biggie. Your q minus 21 just drops straight down. But on the right side, you, once again, kind of like the problem above, the square root of q, and then outside of that plus 7, because that plus 7 is not underneath that radical, you can't just let the square root and the squared just cancel and everything come out of there as q plus 7, because this plus 7 is not under the radical. So therefore, you've got to take the square root of q plus 7 and multiply it by the square root of q plus 7. So let's leave q minus 21 alone at the time, and let's go over here and do this. So first, the square root of q times square root of q really gets people sometimes. Remember, the square root of q times square root of q becomes the square root of q squared. Right? That makes sense, doesn't it? Well, if this is the square root of q squared, all along, haven't we been saying that the square root and the square will just cancel each other? So what does the square root of q times the square root of q end up being? Just q. I hope that makes sense. And again, let me change colors because I need to. And then we got square root of q times positive 7. That's positive 7 square root of q. Remember, I can't multiply that 7 into that radical. Then we change. Positive 7 times square root of q, another positive 7 square root of q. And then finally, positive 7 times positive 7 is positive 49. Now, right here, I can take the 7 square root of q plus 7 square root of q, since they have the exact same radical, and I can combine that to make it plus 14 square root of q. And then, of course, the plus 49. So here's what I'm going to do. Because of the way this problem is, when I start trying to put stuff together, I'm going to subtract this q to bring it over here to this q, and I actually find that they will cancel out. And then I'm going to bring this 49 over by, I don't know what happened there, by subtracting 49, because right now I'm trying to get this q alone. So when I subtract 49 from negative 21, negative 21 minus 49 is negative 70. And that equals 14 times the square root of q. So here's my last two steps. I'm going to divide by 14. That's negative 5 equals the square root of q. Then we're back to solving this square root by raising it to the power of the root. So I square both sides. So I've almost run out of room here, but I'm done. My answer is square root of, or negative 5 squared is 25. Now let's just double check it real quick. I'm going to do it over here to the left because I got a little bit more room over here. I'm going to type in, remember, erase all this crap. I'm going to type these in just like I see them originally. The square root of 25 minus 21. Type that in. You should have gotten 2. Now on the other side, type in the square root of 25 and then scroll outside that radical and put plus 7. You should have gotten 12. Does 2 equal 12? Absolutely not. So this is extraneous. Okay? So hopefully me going through this has helped you understand any of the questions that maybe you ran into. If some of your questions came from the other side and I didn't cover those well enough, hold on to this, and when I come back tomorrow, we'll clarify it. All right, hopefully you already have your notes for today. Your notes, of course, are about graphing. So we're going to jump right into that. If you don't have a graphing calculator, you definitely need one because we are graphing, no doubt about it. So here we go. We're going to use this calculator. We're going to use some of the things that we've talked about quite a bit this year, and that is transformations. We're going to make some transformations. So there's two that we're going to discuss today. First, the square root function. Okay, the square root function in its most simple form, what we call the parent function, in its most simple form, before anything has changed, is simply the square root of x. The square root of x. So let's go look at this in the graphing calculator, and then I'll explain a couple things about it that are important. So let's go to y equals, and let's type in the square root, y'all know where to find that, of x. And let's just graph it. Now, as you can see, here are some things that are important. Where does the origination of this graph start in its simplest form? Right at the origin. And then it kind of goes up, and then it kind of flattens out. Okay, and it'll keep doing that forever. So it starts at its origin, at its most basic form. It starts by going up, and then it starts flattening out as it goes up and to the right. So let's talk about a couple things that are important. All right, first, the endpoint. The endpoint is where the graph begins. That's 0, 0. If anything changes that, it would be considered a transformation. So the endpoint starts for our parent function right there at 0, 0. Now, it wouldn't be bad to graph this to remember that sometimes the nicest place to go is the table. We have 0, 0, which is nice. We also have 1, 1, which is nice. The next nice point looks like 1, 2, 3, 4, 2. And you're welcome to get as many points as you want that are pretty good. Looks like the last one we can sneak into this graph is 9, 3. All right, so I found all the points that I can find from this table here. And this is kind of what the graph is doing. See, it's going up and off to the right. So let's discuss the domain. Remember, domain is what x can equal. X is this direction, right? Left to right. So think about it, guys. Where left to right does this thing start on the x-axis right here? Well, it starts at 0. It starts at a firm 0, okay? And then what does it do? It goes off to the right forever. So it approaches positive infinity. See, we've done this pretty recently, so I think you guys probably have that kind of under control. Now, what about the range? What about the range? What does range mean? Well, remember, range is what y can equal. That's up and down. So going or looking at this graph, where does it start on y? Well, again, it starts at the origin, and that's the smallest place because it goes up, and I know very gradually, but it goes up forever. So it goes from 0 to infinity, just like our domain did. Any change will cause your domain and range possibly to change. It might go the opposite direction. Okay, we're going to look at some different changes that will occur that will cause our endpoint to change. It will cause our domain and our range to change. But I want you to notice something. When it comes to square root functions, your domain and your range are limited. Okay? They are limited. Now, last one, and then we're going to talk about a couple other things. We're going to talk about a cube root function. Now, a cube root function in its most basic form is simply the cube root of x. The cube root of x. So with no changes whatsoever, it's going to be the cube root of x. Anything that happens to that will be a transformation. So hopefully you guys remember to find that. It's math, number 4. Then you're just going to plug x in there and graph it. Okay? So what you do is you kind of see it's very similar to a square root function, except it doesn't just do this part, it does this part as well. Okay? So if you notice this, there's a couple things I want you to pay close attention to. One, it doesn't have an endpoint. See, it keeps on going left, it keeps on going down, it keeps on going up, it keeps on going right forever. Now, it could change directions a little bit based on some transformations, but the point I'm making is it doesn't have an end point, right? So they don't call it an end point, they call it a turning point for a cubic function or a cube root function. So our turning point will be 0, 0, unless it shifts. It might shift left, it might shift right, it might shift up, it might shift down. Remember all that stuff? That could change where that turning point is located. So let's go find a couple of nice points again on our table. You'll notice that when I moved my table earlier, it changed my table for all of these. So let's find a couple of nice points. Obviously, our turning point here was 0, 0. I'm going to mark that one. Then we got 1, negative 1. I'm sorry, we got 1, 1, and we've got negative 1, negative 1. I'm going to go find a couple more points in both directions that are nice. I've got negative 8, negative 2, and I bet you know that we're going to have the same thing in the opposite direction. Let's just go make sure, double check. Sure enough, we have positive 8, positive 2. So let me go look at this with you. So there's what the graph is going to look like. It's going to start down here coming from the left. It's going to make its way up. It's going to do its little turn, and it's going to go on up and to the right forever. So there we have it. That is the graph of a cube root function. So you can tell some similarities. You can also tell some differences. How one keeps on going forever and one ends. In fact, that's what makes domain and range really easy for a cube root function. Look at it. Does it ever stop going left? No. Does it ever stop going right? No. So my domain is unlimited. Now I know it's very gradual, but does it ever stop going down? No. Does it ever stop going up? Also, no. So my range is also unlimited from negative infinity to positive infinity. So that makes those really, really easy. So there you have it, guys. That's what a square root and a cube root function look like. Now, when it comes to all this stuff, we don't generally talk about x-intercepts and stuff like that. We talk more about the endpoint. Sometimes it's called the point of symmetry. We sometimes talk about the turning point. So there you have it. Okay, now we will talk about some other things, and we'll get to that in just a second. But first, let's compare this to some other things that we've done in the past. Look, there are transformations that can absolutely occur, and there are three of them, just like we have a bunch of times. Actually, there's three places where you can have transformations. There are four things, okay? So let me go through these just straight from left to right. Remember, A, this is some number out in front being multiplied. Remember, that actually could be two transformations. It could be two transformations. One, if A is negative, the function is reflected across the x-axis. So the first thing that A could tell you is whether or not that thing's changed the way it's going. Okay, look, let me come back up here real quick. Here's the x-axis, right? So if that A value out there is negative, what's going to happen is it's going to reflect over that x-axis. So that's a transformation that you see if A is negative. But also, A can also represent a vertical stretch if that value is greater than 1, and it can be a vertical compression if that value is between 0 and 1. So remember, I tried to show you this concept a long time ago when we were doing transformations using a hair tie. Right? If that value is greater than 1, like if it's a 2 or a 4 or whatever, that's going to take that square root or that cube root function, and it's just going to pull it up. And it kind of makes it longer up and down. But if that value is like a 1/2 or a 1/3, it actually takes the radical function that you're graphing and it smashes it. It makes it really, really flat. I mean, even flatter than that, if you can imagine. It just squeezes it vertically, and it gets smaller. So that's the two things that A will tell me. It'll tell me if it reflects, but it also tells me if it stretches or compresses. So two things that you learn by A. But then you got this minus H. Minus H is happening where? It's happening inside the radical. Remember, we always talked about how if it happened inside, it's horizontal. Well, that's going to be a horizontal shift. A horizontal shift. Y'all know what horizontal means. It means left and right. Now, I hope that you guys remember this. Because it's on the inside, what did we always say? It's the opposite of what you might think. So if that says x plus 5, positive means it's going to shift left. But if it's x minus 5, that means it's going to shift right. Remember, on the inside, it's the opposite. And that leaves us with one last thing, and that is that plus k. So that's if something's being added or subtracted on the outside. Remember, outside is always vertical. So if that's some value out there, it's representing a vertical shift. It shifts up or it shifts down. Remember what we said about outside? We said it is what it is. So positive would represent an upward shift, and minus, would represent a downward shift. Okay? And that's really all of the transformations. Now, one last little thing. Because of that endpoint or that point of symmetry, or what we called the I probably should have changed it. Instead of calling it a turning point, it was a point of symmetry. We know that that's going to be affected by how that thing shifted. Did it shift left? Did it shift right? Did it shift up? Did it shift down? So what controls the end point or the turning point is the HK value. That's what controls your end point or turning point. Did it shift left, right, up, down? Okay, that changes where that end point is going to be. So I want us to look at this real quick. It says describe the transformations of each function. So let's look at it. Do y'all have anything being multiplied on the outside? Nope. So no reflecting, no vertical stretch, no vertical compression. That's done. Okay, now what about inside? Well, inside we are subtracting 7. So that's a horizontal shift. Now remember the rule? If it looks like a negative 7, it's actually a positive 7 horizontal shift. So it shifts right 7. Okay? Next, we've got this plus 2 outside. That's vertical shift. And it is what it is. So it also shifts up 2. See? Real simple. Okay, number 2. Look, you've got an A value out there. It's 4. Not negative, so no reflection, but 4. That's definitely greater than 1. So what that's going to do is it's going to grab that cube root function and it's going to pull it vertically upward. So we call it a vertical stretch. Vertical stretch. Okay? Now, is anything being added or subtracted inside? No. So there's no horizontal shift. This minus 1 is clearly outside the radical. So that is a vertical shift. And it is what it is. So it shifts down 1. Okay? Pretty easy, I hope. Look at number 3. Look, we got a negative out there. So this thing is going to reflect over the x-axis. We also got that plus 3 inside, so it's the opposite from what we might think. So it's going to shift to the left 3. Okay, over here to number 4, we got that 1/2 out there. No reflection, but that 1/2 is smaller than 1. So that's going to be a vertical, what? A vertical compression. That thing's going to get even flatter. This is a square root graph. It's going to get even flatter. Now right here, that minus 2 inside, that is going to be a horizontal shift. And remember, it's the opposite of what it might look. So it's going to shift right 2. And then outside is what it is. And it's vertical, so it's going to shift down 6. Okay? So there you have it. There's numbers 1 through 4 on the front. Let's go to the back. This just wants me to actually do one myself. So watch how I do this. It says a square root parent function. Okay, square root. So I know it's a square root. I know I got an x in there. It says it's reflected across the x-axis. Remember, that's a negative on the outside. Then it shifted 7 units left. That is a horizontal shift, right? Horizontal is inside. So it's the opposite. When I think of left, I think of negative 7. But remember, it's the opposite, so I'm putting plus 7. And then it says it shifts 1 unit down. Remember, that's on the outside. It is what it is. So down 1 means minus 1. So there it is. I just came up with that pretty fast, didn't I? Pretty easy. Next one is a cube root function. Go ahead and put my x in there. It says it has a turning point located at negative 2, positive 3. Remember, guys, this is your h and your k. So if my h is a negative 2, that means it went left 2. Well, left 2, I think negative 2. It says negative 2, but we know that on the inside it's the opposite, so it's going to be a plus 2. And then on the outside it says positive 3, so we know that it's going up 3, so it is what it is. So there you have it. It's a cube root function that has shifted left 2, so plus 2 inside, and up 3. And that's it. That's all there is to that one. Okay? All right, a couple graphs. We got about 5 minutes or so before this video probably needs to end. We're at 35 minutes right now. And I want to go to your graph. I want you to notice this real quick. Really, this is just a parent function, but it's added 5 on the outside. So I hope that you guys might know that that means it's taken a square root function and it simply shifted it up 1, 2, 3, 4, 5. So I bet you anything, my endpoint is definitely going to 0, 5, right? Because it didn't shift left, it didn't shift down, it only shifted up 5. Let's go check it out. So I'm going to type in the square root of x. I'm going to scroll outside of that so it closes that radical off, and I'm going to do plus 5. I'm going to graph it, and sure enough, it shifted up 5. Now let's go find another couple of nice points here. We know it's at 0, 5, right there. It looks like 1, 6 is a pretty nice graphing point. We got 4, 7, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, and I really think 3 is way plenty. So here's what we got. We got a graph going up and to the right, just like this. So guys, what's my domain? Where does it start from left to right? Well, it starts right here at 0, doesn't it? That's the smallest value of x I could possibly have. So it's going to start from 0, and it's going to go off to the right. See, it goes off to the right forever. So 0 to infinity. Okay, how about my range? Let me erase that. My range, remember, is y. It doesn't start below that point. What is that point? Positive 5. And it goes up forever. Now, real gradually, but still, hey, it's going up. Okay, so let's talk about end behavior. Y'all know this. As x approaches infinity. So look, guys, as x goes off to the right, what is y doing? It's going up. So as x approaches infinity, y also approaches infinity. So that's really simple. Y'all have done this, and y'all did pretty good on this. Now look at this. As x approaches negative infinity, what is y approaching? Does y ever, as it goes off to the left, does y keep going down? No. Y approaches negative 5. Okay? It's always approaching that endpoint on y. And since my endpoint, look right here, look where my mouse is. Since my endpoint is 0, 5, that's what tells me that it's approaching negative, I don't know why I put negative 5. It's approaching positive 5. Let me erase that. I don't know what happened there. And then, of course, the increasing, decreasing intervals. Look, isn't it always going up? So it really does not have a decreasing interval. Look at it. Radical functions never really go down unless it's flipped upside down. So this one's only going up, and it's going up from the beginning of where it starts, which is at 0 forever to the right. So there you have it with graphing radical functions. So let's go to the, those are all, man, they all ended up being, oh, here's what I ended up doing. We're going to change this one right here. We're going to change this to the cube root. Go ahead and change number 8. And we're going to do the cube root right here. And this is what we'll finish on. So everybody change number 8 to the cube root of. And let's go to our calculator. Let's go math, number 4, x minus 1. Go outside of the radical and put minus 4. Now, before I graph this, I want you guys to recognize something. Look at my mouse. What is this telling me? Horizontal shift. It's shifting right. Remember, it's the opposite. Right 1. And this is telling me it's going down 4. So I should already know. Look, I should already know this thing is going right 1 and down 1, 2, 3, 4. That should be my new turning point, my point of symmetry, at 1, negative 4. Now let's go graph it and see if I'm right. Sure enough, look, 1, negative 4, you clearly see that's the middle of the graph. Now let's go find another couple of points. I'm going to go put 1, negative 4 right in the middle. There it is. I've got 0, -5. I've got 2, -3. Let me find another one in both directions. Let's see here. Let's go down for a minute. Let's see if we can find one soon. There's one. 9, -2. And let's go up some. Oh, wait. Pushing the wrong button. Let's go up and see if we found another one in the other direction. There's one. -7. 1, 2, 3, 4, 5, 6, 7. Positive or -6. Okay, I've marked all these points on my graph, so let me show you. This is what I have. Hopefully yours looks the same. So look at this thing. It's going up, kind of does that little curve, keeps going up. So remember, what about domain and range? It's unlimited in both directions because it's a cube root. Range, it's unlimited up and down. It's unlimited left and right. So what about in behavior? As x goes off to the right, what is y doing? Well, it's going up. So as x approaches infinity, y also approaches infinity. And to the left, as x goes off towards negative infinity, what is y doing? Well, it continues to go down. So it also approaches negative infinity. So that's real simple. And then this one, the increasing or decreasing, remember, look at it from left to right. It's going up, going up, going up, going up steeper, going up steeper, going up, going. It never starts decreasing. The only thing that would make it decrease is if it reflected. So this one is only increasing, and it's increasing forever. So it never decreases. The only time it'll decrease, like I just said, is when you have a reflection. So here's what I want you guys to do for your homework. Okay, on this homework that is about to be passed out, I want you to do numbers 1 through 4. Okay, all of these 1, 2, 3, 4, and then I want you to graph number 6. Flip it over to the back. I want you to do number 8, and I want you to do number 10. Okay? So here's what you got. You got 1 through 4, 6, 8, and 10. So that's 3 graphs. Okay, that's 7 problems. I think you guys will do well. If not, again, we'll adjust. Also have the review printed out and prepared and ready. If you want to go ahead and take the review to go ahead and start studying for your test that's going to be Thursday or maybe Friday, just ask Miss Story and she'll give them to you. If not, I'll give them to you tomorrow. Okay? Hope you have a great day. See you soon.